So in the case of a mechanical wave in a string, that's a sinusoidal wave, we have seen that the kinetic energy and potential energy are equal and found to follow a relationship that is kinetic energy or potential energy K is equal to potential energy U, that is equal to 1 by 4 lambda mu U0 square, where mu is the linear density, lambda the wavelength, and U0 is the maximum velocity, which follows, say, U0 equal to 2 pi nu A, where nu is the frequency and A is the amplitude of the wave. Then the total energy E will be the sum of the kinetic energy and potential energy K plus U, that is 1 by 4 lambda mu U0 square plus 1 by 4 lambda mu U0 square, that is 2 into twice of this quantity. 2 and 4 make it, say, 1 by 2 lambda mu U0 square. Thus we conclude that the total energy E is equal to half lambda mu U0 square. So lambda and mu has their usual meaning, and U0 is the maximum velocity of the wave. Now we'll see the transport of energy by a wave. A wave by definition is a mode of disturbance that is propagating in a medium, and this disturbance is essentially energy. So as a wave propagating a medium, energy will be distributed in the wave. We will now consider the amount of energy distributed, and energy by definition is the capability to do work, and according to the work energy theorem, the energy can be measured in terms of the capability for work being done by the wave. So we will have a very primitive derivation in which we will evaluate the work done by a wave. And the work is always the product of force and displacement. If you are having a continuous force, then the work done can be evaluated as the integral of the small work done by this force. For that, once again consider the wave equation. Y is equal to y of x comma t, of course, which is a function of x position and the time point. Y is equal to a sine 2 pi mu into t minus x by v. When x equal to 0, that is the initial point of observation, y0 will be equal to a sine 2 pi nu t, because x is equal to 0 in this bracket, and the bracket converges to, say, simply t. The component of force, because we are interested in evaluating the work done, work is equal to force into displacement. If you are evaluating a small work done by the wave upon making a displacement through an extremely small distance, say dy0, I have some problems with my pointer, sorry. Then dw is equal to f into dy0, and the work will be done in the transverse direction, that is in the upward direction, in which the particles of the medium will be undergoing a displacement. So the vertical component of the force, or the transverse component of the force, needed to be taken into consideration. For that, consider the wave propagating in this manner. The tension will be along this direction, so that the force acting will be opposite to it. The force or the tension also will have two different components. Suppose this tension make an angle, say theta, with the horizontal direction, which is the same as the inclination of the wave disturbance with the horizontal direction. Then tension will have two components, say t cos theta along this and t sin theta along this. The force also will have two components, say f cos theta along this and f sin theta along this, which will be the y component of the force, which will be balanced by the y component of the tension. Since these are opposite in direction, we have Fy, the transverse component of the force, is equal to minus t sine theta. And by definition, sine theta is the slope of this curve, which can be evaluated as a dy by dx at the point where you are making this observation. For the time being, it is at, say, x equal to 0. So the transverse component of the force is minus t dy by dx at x equal to 0. We will now evaluate this dy by dx. Since we have y is equal to a sine 2 pi nu into t minus x by v, dy by dx will be equal to a into derivative of this sine term, that is cosine of 2 pi nu into t minus x by v into derivative of minus x by v, that is minus 1 by v into 2 pi nu outside this bracket. So overall I have 2 pi nu by v with a minus sign outside. Already a is here, which is written here minus 2 pi nu a by v into cosine of 2 pi nu into t minus x by v. Therefore, the tangential component of a force, which is Fy equal to minus t sine theta equal to minus t dy by dx, is minus vanishes, this minus vanishes with this minus, and 2 pi nu a t by v cos 2 pi nu t will be the expression for the tangential component of the force. Let it make an extremely small displacement for y at 0, say d by 0, then the work done in this, in terms of an extremely small amount, dw is equal to Fy into d by 0. Then the overall work done by the wave over one complete cycle or over any desired range of displacement can be evaluated as the integral of this work, because work W is equal to integral dW. We will evaluate this as an indefinite integral, as it has the provision of evaluating this work done over any desirable range of interval. So W is equal to integral Fy d by 0. Fy is this one, 2 pi nu at by v. 2 pi nu at by v is constant and is taken out of the integral. What remains is integral cos 2 pi nu t into derivative of y at x equal to 0, which we have already found as a sin 2 pi nu into t. So derivative of a sin 2 pi nu into t. Derivative of a sin 2 pi nu t will be equal to a into cos 2 pi nu t into derivative of 2 pi nu t, that will be, say, 2 pi nu into nu t dt. Sorry, 2 pi nu t will not be the derivative of the t will be dt. So we substitute it here. Fy has a constant part 2 pi nu at by v, and from this I have 2 pi nu a coming out. So overall make it, say, 2 pi nu a whole square t tension divided by v integral cos 2 pi nu t into sin 2 pi nu t has a derivative again cos 2 pi nu t dt. So make it, say, cos square 2 pi nu t dt. This we have integrated several times. This will contribute only, say, 1 by 2 integral dt, making it, say, t. So we can express this more simply. I have one more step here. By recognizing that 2 pi nu a is the maximum speed, u0. So we substitute 2 pi nu a as u0. 2 pi nu a whole square will be u0 square t by v integral cos square 2 pi nu t dt. Now we will evaluate this integral now as a definite integral over some desired range. As let's evaluate this work done for one complete period. One complete period will have a time variation from 0 to 1 by frequency. 1 by frequency is time period. So time period we take it, say, small t. When we have a work done over one complete cycle, u0 square t by 2v integral 0 to 1 by t. I have a cos square term here. This I decompose as a 1 plus cos 2 theta by 2. And that by 2 is written here. And 1 plus cos 4 pi nu t is there in the bracket times dt. Now this integration we have performed several times. This contribute only 1 by 2 integral dt, making it, say, t. From 0 to 1 by nu, making it, say, 1 by nu. So u0 square t by 2v, this term is here. And integral dt over 0 to 1 by nu will be 1 by nu. And this 1 by nu is written here. So work done in a complete cycle is u0 square t divided by 2 nu v, or t2v nu, where v is the wave velocity and u0 is the maximum wave velocity. Substitute t equal to mu v square and v equal to nu lambda or nu equal to v by lambda. This expression becomes 1 by 2 lambda mu u0 square, which I have evaluated several steps before as 2 pi square nu square a square lambda mu. By simply substituting u0 is equal to 2 pi nu a, this work done is proportional to square of the frequency, square of the amplitude of the wavelength and the linear density, which are just twice the values of the kinetic energy and potential energy per wavelength. And the rate of doing work as described by the mean power input is obtained by taking this equation, say u0 square t divided by 2v nu for the work per cycle, and multiplying this by the number of cycles per unit time, which is nothing other than the frequency nu. Thus, the work delivering capacity or the rate of doing work, or so-called power, is equal to u0 square t by 2v only, nu the anxious, that is half mu u0 square v, because t equal to mu v square. We make that substitution here, t equal to mu v square, and we find that the power is equal to half mu u0 square v. This is the power delivering capacity of a wave. Besides the power or the energy, the wave carry momentum also. This is something taken to be very cautiously, because momentum is the capability of producing an impact. We have seen that waves will be causing impacts, however, and waves are not only associated with energy, they are associated with the momentum also. Generally, momentum is the property associated with particles, however, waves are also capable of making some impact, which is measured in terms of the physical quantity referred to as momentum. So we now make a statement on the momentum flow and mechanical radiation pressure of a mechanical wave. So energy transport is evident as long as waves are taken into consideration. Energy cannot be separated from momentum, because energy is directly related to momentum, as energy equal to p square divided by 2m. So whenever there is energy flow, definitely there will be momentum flow. Energy transport is associated with the momentum transport. The ratio of the energy transport to momentum transport is normally the velocity v. However, in the case of a wave, it's difficult to evaluate. Calculation of the wave momentum involves a detailed consideration of the particles of the medium or the properties of the medium. Perfectly elastic medium generally do not exist, unlike in the case of particles. In the case of particles, these are more or less perfectly elastic, such that momentum transfer and momentum flow is a master quality of any particle system. However, that is not so observable in the case of waves. A question closely relating to the momentum flow is the mechanical force exerted by waves on an object that absorb or reflect them. Is well established. For example, the longitudinal wave in a gas exert a pressure on the surface of the wall. It can be experienced, however, the quantification is a bit different. You can evaluate this in terms of the universal gas theory as an evaluation of the pressure exerted by gases on the surface of the walls. In a similar way, waves are also capable of causing some effects of pressure at the interface of material media, which can be evaluated as a momentum flow. So, practically, momentum flow associated with a wave can be taken as the or is observable as the mechanical radiation pressure. So, with this, we would like to come an end for this energy flow and momentum flow as long as mechanical waves are taken into consideration.